You see, I have to clear my throat, otherwise the mic doesn't activate, and the first couple words I say don't get picked up. Hopefully you can hear this. This video will serve as our first detailed look at and analysis of a heat engine using its PV, the cycle in the PV diagram, and all the equations that we've been looking at for the last couple chapters. So just about everything covered in those previous thermodynamics chapters shows up in these problems. So if you didn't learn that stuff, you're going to have to go back and pick it up. Okay, there's a couple facts I should review. One of them is that the work done, well here, the first law of thermodynamics says that there are two ways to change the internal energy of a thermodynamic system. Let's just consider it to be a volume of gas. You could either transfer heat in or out of it, or you could do work on it. So when you write the first law in this form with the plus sign and the delta E on one side, it's understood in your book, this is the work done on the gas. So if you're compressing the gas, this is a positive quantity. If you're allowing the gas to expand, then the environment is actually doing negative work. This would be a negative number. Or you could say that the gas is doing positive work. So different books use different sign conventions. In this chapter, your book chooses to use a different convention because it's actually more convenient in the context of analyzing a heat engine. So instead of talking about the work done on the gas, let's talk about the work done by the gas or by the system. So your book uses the notation WS for work done by the system, and it's always the negative of the work done on the gas. So this was used in chapters, let's see, I guess that would be 18, 19, 20. And now we're using this in chapter 21 because the emphasis is on heat engines. You should memorize this. And if that's the notation you use, the first law looks a little bit different. Q minus WS, right? Because W would be the negative of WS. So this is perfectly valid. Some books would get rid of the subscript S, and then it's understood this is the work done by the gas, not the work done on the gas. And let's rearrange this to say that Q is WS plus delta E. And this is a useful way of thinking about it for the working substance of a heat engine, whether that's a liquid like water, which is maybe undergoing a phase change, or an ideal gas. And here's why. Because usually in a heat engine, you're burning something like coal, gas, oil, or you're even fissioning nuclei of atoms. And that means you're releasing a whole bunch of heat into the system. And that heat can be used for a couple things, or it can show up in a couple ways. Either it's being used by the gas to do work, right? You dump heat into the gas within the automobile engine cylinders, and that gas expands and does work, or it raises the temperature of the gas and hence its internal energy. Those are the two ways that energy or that heat can show up. It can either lead to the gas doing work on its surroundings, or it can show up as an increase in the gas's thermal energy. So maybe this is a more intuitive way to think about it for you. I think it is when you're dealing with heat engines. So we'll be using this to solve this problem. Also, remember that the work done on a gas is the negative of the integral of P dV. This quantity, remember, P dV is like F dx. If you think back to 3a and the infinitesimal amount of work done by a force applied through a distance dx, since the work done by the system is the negative of the work done on the system, then in this chapter, we're going to use the plus sign. It's the integral of P dV from V initial to V final. It's the area under the pressure versus volume curve. In other words, the PV diagram. So you should know this from your reading already, but suppose you've got a gas at a particular pressure and temperature. Here's the pressure axis and the volume axis. So the gas starts out in this particular state on the PV diagram, and then if it's an ideal gas, if you know P and V, you could presumably solve for the temperature if you knew the number of moles. So let's say the gas expands in some particular way to this place, this particular point on the PV diagram, so that this is initial volume, this is final volume. Well, the area under the P versus V curve is this area right here. So the work done by the gas in going from here to here, since it's expanding, that's going to be a positive area. Think back to first semester calculus. If you integrate from a number on the real line to a greater number on the real line, and your curve is up here, not down here, that area is positive. But since we're talking about heat engines, whatever the working substance is, whether it's a mixture of air and fuel or steam, it's got to be a cyclic process. The pistons or the cylinders in your engine, I should say the pistons actually, they go up and down, thousands of times per second. Everything is cyclic. So the state of the gas must return to what it was originally. So this thing's going to not necessarily retrace its steps. In fact, that would be useless, we're going to see. But it's going to make its way back somehow to its original state so that it can start over and repeat everything. Now, on the way back, you guys remember in calculus, if you integrate from a real number to a lesser real number, even if the curve is above the axis, the horizontal axis, that's considered to be a negative value. That's a signed integral. It's got a minus sign. So let me put hatch marks in a different direction. And I didn't make this bold enough. There we go. So now I'm hatching in the area under this bottom curve, and we're going this way along the PV diagram, or the trajectory in the PV diagram. So this area is negative. Well, the total work done by the system, you probably didn't see this in first semester calculus, but you could put this little circle symbol here to mean that you're integrating around a closed path in the PV plane. It's like a line integral. Don't worry about the details because computationally it's always very straightforward. What happens if you take the positive area and under this top curve and add the negative area under the bottom curve? In other words, take the top area and subtract the area under the bottom curve. Of course, what you're left with is everything in between. So there's that really simple, satisfying graphical interpretation for the work integral. It's merely the area enclosed by the PV cycle, or the PV curve in the PV plane. So you can just look at that area and get some sense of how much work is done. If the return path coincided with the initial path, there would be no area enclosed. That would be a useless engine because it wouldn't be doing any work. Now, your first thought might be, great, let's just look for the shape that encloses the largest possible area. You could pose the question, okay, for a given arc length, let's say you've already specified that the arc length total has got to be like 10 centimeters on this piece of paper. What's the shape that would result in the greatest possible work output? Because that sounds good, an engine that can do a lot of work. And maybe you've got some common sense here, or maybe you've heard this before, that it turns out this is a problem from antiquity. I think like thousands of years ago, people wondered this. There's some legend about a queen offering money to anybody who can answer this question or prove it. You know, if you've got a certain number of yards of fencing, what's the shape that will enclose the largest possible piece of land? It's a circle, not surprising. I mean, what else could it be? Anything else you can think of seems silly. Of course, it's a circle. But just because the curve might enclose the largest possible area doesn't actually mean that the engine's the most efficient. Because what you can't see easily, you can't just look at this graph and be able to tell how much heat had to be absorbed by the high temperature reservoir. Remember, this is really all about practical stuff. This whole science was developed so that engineers could design better and better heat engines. Ultimately, you have to pay for the fuel. That heat QH, which is absorbed from the high temperature reservoir, you got to pay for that somehow. Somebody has to dig up the coal or get the frack to get the fossil fuels out of the ground. So it's more about efficiency than total work output. And you can't tell efficiency just by looking at the graph. Maybe there's some way, and I have not studied that, but it would be neat if you could somehow prove what the particular shape is that has max efficiency. Actually, I know the answer because it's in your book. And I believe it's the Carnot engine, 2 adiabats and 2 isotherms. But we'll get to that later. Okay, so I think we're ready to begin. All the other relevant formulas that we need have been covered in previous chapters. So let's jump right into the problem. And I will warn you, I'm going to go about this in depth here. We'll beat this problem to death. I'll be as thorough as possible so that you can go back and watch it and rewatch it at your leisure and consider this good practice for one, maybe even two exam problems. You will definitely have a heat engine problem on your exam where you have to use the PV diagram, all this garbage we've been looking at for the last few chapters. Okay, understanding this picture might actually be the most difficult part of the problem. I think it is. We've got a quantity of gas here inside this cylinder, and they tell us that there's a pin supporting the piston here. So the gas itself does not have to support the weight of the piston plus the masses on top. And that likely means that the pressure in here is not necessarily equal to the atmospheric pressure up here plus the way the weight is distributed. So there's a formula that I don't think I've addressed yet. It shows up in a couple problems. First of all, I want to point out, if it's 1 atmosphere of pressure in here, that means that the pressure up here is actually not 1 atmosphere, because the think about the total push downwards due to the air up here and the weights. You've got the atmospheric pressure plus the weight of these masses, which is distributed over the piston. Those two together are going to add, or those three, because there's 2 masses, those would add up to a pressure greater than just atmospheric pressure. So that alone tells me that the pressure up here is not 1 atmosphere. And that kind of threw me off a little bit, because usually when they draw a picture like this, you just assume that the pressure here is atmospheric pressure. But I guess we're at the top of Mount Everest or something where the pressure is less than 1 atmosphere. So let me write down that equation real quick. Just on the reverse side, just ignore that. Here's the picture I'm talking about. This is supposed to be a piston that's free to slide. There's some masses sitting on top of it. The air in here, the air pressure must support, or the gas pressure must support, not only the weight of these masses, but the pressure from the atmosphere above. So I'm just going to use the letter M for the total mass of these 2 chunks. Let's just call that total mass M. That total mass M has a weight, mg, which is distributed over an area A, where A is the surface area of this piston as you're looking down. So this is the contribution to the pressure due to the weight of all this garbage. Plus, you also have to support the atmospheric pressure above. Just think of it as a pushing contest right here. Think about like a line of molecules right here. They're being pushed up due to the pressure within the gas, but they're being pushed down by the weight of these masses and the atmosphere above. And those 2 pushes have to equal if this line of molecules is going to be in equilibrium. So in other words, the interior pressure P has to equal the weight of the masses distributed over the area of the piston plus atmospheric pressure. This does show up in a couple places. We don't actually need it for this problem, but I went over it so that you can better understand this picture. So the point is, that condition does not need to be satisfied if you have the pin here. Let me get the laser pointer. Okay, here's my laser pointer. The pin is what's supporting the weight of these masses and the air above. It's not necessary for the pressure down here to satisfy that condition I just wrote down. Okay, 20 degrees Celsius, we're talking about 293 kelvins. They gave us the volume. So we're given the initial P, V, and T. We can use the ideal gas law to solve for N, the number of moles. So we know all the state variables for the first point on the PV diagram. We'll look at the PV diagram in a moment. Then we're told that the pin is still in, and we put a flame under the gas and heat it up. Now, if the volume remains fixed, I always think back to that PhET simulation with the particles bouncing around. If you're increasing the temperature, that means all the particles are bouncing around faster. That means they collide with the walls more often, so the pressure goes up. We know the pressure is going to go up. How much? Well, they tell us it goes from 1 to 3 atmospheres. So that the pressure is tripled, and you can do this right now in your head. How much would the temperature have to go up in order to triple the pressure? Well, we can do this with the ideal gas law, but remember, it's all proportional reasoning. Since if the volume is fixed, the only way to triple the pressure would be to also triple the absolute temperature. So we'll write that down, but that's easy to do in your heads. Or in your head, you only have one head. Okay, then the pin is removed. So what's going to happen Yeah, actually, they tell you this in the statement of the problem. So this is not at all obvious from the diagram. You would not be able to do this problem just by looking at the diagram. You need this extra information. They tell you that the pressure here, 3 atmospheres, is just enough so that once you remove the pin, this thing keeps floating there, or it's, it's balanced. And that means that the condition I wrote down would be satisfied. Let me go back to that. Yeah, so once the pin is removed, that 3 atmospheres of pressure is just enough to balance the atmospheric pressure above, which we already concluded in this problem is not actually 1 atmosphere. I think that's confusing. Plus the extra pressure due to those weights sitting on the piston. Okay, back to PowerPoint. But then you continue to heat, and now because the pin's not in, this thing is free to expand. Now, why would they do it that way? What type of ideal gas process is it if the piston is moving slowly upwards as you heat the gas? You should just try to learn that that is an isobaric process. Because think about it, the atmospheric pressure up here is not going to change, and the weight of these masses is not going to change. So if you think about that tug of war on the layer of molecules at the top here, the downward push doesn't change, and that means the upward push cannot change as this thing is free to slide upwards. So that tells us that the pressure in here is constant. So going from here to here is an isobaric process. That's going to be a horizontal trajectory on the PV diagram. You see how interpreting the picture is one of the most difficult parts? It requires some imagination, and that's going to take practice. Once the piston gets up to the top, you stick a pin in again, and then you unload the mass. And now you see the whole purpose of this. The whole point of a heat engine is to do useful work. So this is kind of silly, but instead of like a regular size cylinder, instead of this being like a Coke can, imagine it's the size of an elevator shaft, and you live in some primitive society where you figured out how to seal off this chamber and build a fire underneath the chamber, and you use the expanding gases to lift, I don't know, boxes of rocks up to the top of a cliff, because who wants to haul those rocks to the top of the cliff by hand? That's a pain. Let the gas do it for you. Let the dead dinosaurs and plants do it for you, because remember, that's what fossil fuels are. When we burn gasoline, we're just ripping through like millions of years of stored energy from the sun. That's not like a Fern Gully criticism there of our modern industrial world. It's just an observation. Okay, so the whole point of the engine is right here. You've done useful work. The gas is expanded and done work on the environment. And most directly, it's done work on the piston, but the piston's pushing on the masses, and now you've got your box of rocks at the top of the cliff. Yay. Well, if you want to do that again, you've got to get the piston back to where it was at the beginning so that you can lift another rock. The whole thing needs to be cyclic. So first, the pin is left in. Remember, we're at 3 atmospheres, right? This whole process was isobaric. We're still at 3 atmospheres. We need to get back down to 1 atmosphere. So you put some ice, you get rid of the fire, you put some ice there to cool down your gas. And once you're back down to 1 atmosphere, then the pin is removed again. And here's another piece of information in the problem. You wouldn't know this just by looking at the diagram, so you do have to read the problem. They tell you that when the pin is removed here, the pressure, 1 atmosphere, is just enough to maintain equilibrium. So this thing doesn't fall rapidly. It's already in equilibrium. The gas inside is pushing up just as hard as the atmosphere is pushing down with the weight of the mass. So to summarize, up here when the pin is taken out, evidently 3 atmospheres is just right to support the weight of this piston and the weights and the atmosphere. Down here, 1 atmosphere is just enough to support the weight of the piston and the single mass and the atmosphere above. That's one of the more nuanced parts of the problem. Once the pin is out, the gas continues to cool because it's in contact with the ice. So that means heat is flowing out here. This is where we dump heat to the cold reservoir, right? Up here is where we extract heat from the hot reservoir, and then down here we exhaust heat to the cold reservoir. That's what an engine does. And by the same argument that I made earlier, this is an isobaric process as well. This piston's going to gradually come down. At all times, the downward push from the weight and the atmosphere is equal to the upward push of the the gas, but because that downward push doesn't change, that means the upward push doesn't change. That means it's always 1 atmosphere throughout this time. Finally, when you're back down here, you stick a pin in it, you plop your new box of rocks on the piston, and you're ready to start over in a cyclic process. All right, I think that's the hardest part. Now that that's out of the way, we can look at the PV diagram. I took this from your solutions manual and I added some terms here. So let's just switch back and forth between the previous picture and the PV diagram to make sure we can make the connection. The first step, the first process, we go from point 1 on the PV diagram to point 2. So notice we're at 1 atmosphere and 50 milliliters. Let's confirm, yes, those are the conditions they gave us. And then because the pin is left in, the volume doesn't change, but we dump heat into the gas, and that means the pressure is going to go up because the temperature will go up. The particles are bouncing around faster, pressure goes up. Since the volume is not changing, that's what we call a constant volume process. In other words, an isochoric. Oh, darn it! Look at that typo. This says isobar. Let me fix that. Focus poof. There it is. Isochoric. So constant volume, also known as an isochoric process. Or you could just call the curve an isochore. And how do we know that the pressure goes from 1 to 3 atmospheres? That was labeled in the diagram. Okay, now what state variables do we know at this point? Well, it's a PV diagram, so of course we can read P and V off of the diagram. T is not specified. They told us what T was at point 1. It was 20 degrees Celsius or 293 kelvins. This one we would have to calculate. So you could either use the ideal gas law. If you already had calculated the number of moles, you could plug all that stuff in to solve for T from the ideal gas law, or you could use proportional reasoning. And I'll do that in a moment. And the next part, the isobaric process, let's look again. That's from 2 to 3. Remember, the pin is removed, and gradually we continue to heat up the particles. So they tend to expand, or the gas tends to expand. It's doing work on its surroundings. That's where the useful work comes in. But heat is still going into the gas. So if we look at 2 to 3, definitely useful work is being done. I mean, look at the area under this curve. If you're going from left to right, that's positive area. So work is being done. But at the same time, heat is flowing in. So we're going to, when we solve for Q and WS, the work done by the system, both of those will be positive quantities. So I think we've just established that Q sub H, the heat drawn from the hot reservoir, actually happens during 2 processes. Positive heat flows in here and here. We're going to have to add those up. That will be Q sub H. Now maybe you're wondering, what is the reservoir exactly? Sometimes it's obvious and sometimes it's not. In this case, the reservoir would be the flames, the air surrounding the flames. That's going to be much hotter than, presumably, than the air inside the cylinder. We will actually solve for the temperatures, but they're not going to be anywhere near the temperature of the flames. So the flames, those are the hot reservoir. Cold reservoir, of course, would be the ice. Okay, 3 to 4. Go back here. That's an isochoric cooling. That would be from 4 to, oh yeah, isn't that annoying? Look, the numbers on this diagram do not correspond to these numbers here. 1, 2, 3. Where's my laser pointer? Yeah, that's unfortunate. These numbers do not correspond to the numbers on the PV diagram. That's okay. Let's not worry about the numbers. While the pin is in and we put the ice under, that's when the temperature is going to go down, the pressure will drop, but the volume doesn't change. That would be from here to isochoric drop in pressure. Now the last isobar, that's after you've taken the pin out and you allow the gas to continue cooling gradually, and the piston will fall, all the while the pressure in here matches the pressure due to the weight and the atmosphere above. I keep doing that. Come on, what am I doing? That's this last isobaric process here. Okay, and then when we return to position 1 on the PV diagram, we are right back here. Okay, 2 isobars and 2 isochores. Okay? That's probably not a particularly efficient engine. And I'm going to point out something here. Don't be intimidated by any of these heat engine problems, because if it's an arbitrary curve that's drawn, we can't do anything with it. I mean, if I just drew some random squiggly process, we would have no idea where to start. So every process in a PV cycle that you could possibly analyze is going to be one of these familiar curves. It's going to be an isobaric process, an isochoric, or an isotherm. I think that's it. Or an adiabatic curve, right? Adiabatic. So there's 4 possibilities for each side. So any combination you can think of, you could analyze that. You've got all the tools. Heck, you could make up a problem for yourself. Just draw a closed figure that's composed of some combination of isobars, isochors, adiabats, and isotherms. You've got the tools to analyze it. All you need is first law of thermodynamics, the definition of work, the definition of constant volume heat capacity, the definition of constant pressure heat capacity. What was the other one? There's some other, the ideal gas law. I believe that's all you need. And then you have to know about the equipartition theorem so you can decide what your heat capacities are, your molar heat capacities. But let's proceed. So I've redrawn the cycle on the PV diagram. I've labeled the points just as they were, I think they were listed in the problem, or at least in the solutions manual. The volume axis is not in SI units, so it's up to us to convert. And remember, 1 cubic centimeter, that's 10 to the negative 2 meters cubed, which is a millionth of a cubic meter. Now, something I like to do is to draw the isotherms through all the points. So off the top of my head, I don't remember what the temperature is. No, they told us this first temperature, isn't it 20 degrees Celsius or 293? So I'm just going to make a very rough sketch of the isotherm, that hyperbola, and I'll label it 293. And I forget if these two fall on the same isotherm. They probably don't. So in general, we're going to have 3 more isotherms, and I'll wait to sketch those. But that kind of helps me visualize the change in energy, because remember, for an ideal gas, the energy depends only on the, for constant number of moles, it depends only on the temperature. Okay, now you know me, I couldn't resist implementing a spreadsheet. So I'm going to use Excel to solve this problem. And I'll be switching back and forth between the spreadsheet and the notes here. But the whole point here is to calculate the efficiency of this engine. Well, efficiency, remember, is the useful output work divided by how much heat total was absorbed from the high temperature reservoir. This is what you have to pay for in the form of coal or gas, whatever, natural gas. This is the useful work that you do, in this case, lifting those boxes of rocks. You want to get as much possible, or as much useful output as possible for whatever you're paying for. So this is a sensible definition for efficiency. So that means we're going to have to find the heat absorbed here and the heat absorbed here and add them up to find the total heat absorbed. And we also have to calculate the work done. Now the work done, that's so easy. I'm going to do it 2 ways, but the first way is trivial. The output work, remember, is the area enclosed on the PV diagram. So sometimes that's the easiest possible thing to calculate. Excuse me. Now, if these were adiabats, no, you wouldn't have any simple formula. This is just a square. It's trivial. So that's just going to be base times height. Well, it looks like a square. It's a rectangle. So I'll call that delta P times delta V. The pressure goes from 1 to 3 atmospheres. So that's a change of 2 atmospheres times 1.013 times 10 to the 5th. Remember, it's 100 kilopascals. Pascals per atmosphere. That's my change in pressure. It goes from 1 to 3. And the change in volume is from 50 to 100. That's also 50 millionths of a cubic meter. So calculating the useful output work was so easy for this problem. $50 millionths, and I get 10 joules. That's not very impressive. Okay. This heat engine in 1 cycle does 10 joules of work. Well, depending on what kind of engine this is, maybe like your car engine, it's going through thousands of cycles per second. So that 10 joules may not sound like much, but multiplied by, I'm sorry, your car does thousands of cycles per minute, not second. Anyway, this could be a significant output power depending on the frequency at which the engine turns over, so to speak. Okay, this is going to be another matter. We're going to have to use our formulas from previous chapters. So I'll do some of this on paper here. Let's first look at process 1 to 2. Keep these side by side. Process 1 to 2. All right, what can we say here? Well, it's an isobaric process. The change in volume is 0, so the work done by the system is 0. Remember, work done by the system is the integral of pressure with respect to volume. Will be, what's the area under a vertical line? There's no area under that curve. So that's easy. Anytime it's an isobaric process, jump straight to that. Work done is 0. And then from the first law, I'm going to use our new version of the first law. Yeah, that says LAW there. It says that the heat absorbed by a gas can show up in 2 ways. It can be used to do work by the system or to change the system's internal energy. Now, we've just established that for this process, the work done is 0. And let me pause to make a very important point. Yes, Q can be a positive or negative number. If heat's flowing into the gas, Q is positive. If heat is flowing out of the gas, Q is negative. On the other hand, Q sub H is always a positive number. Q sub H and Q sub C are both positive numbers because they refer to the absolute values of the heat. So what you'd have to do is find, for all these steps, find the various positive Qs, add them up, and those would be the heats going into the gas. So presumably that's the heat with the heat taken up from the hot reservoir. You would add those up to get QH. Some of the Qs are going to be negative though. When the heat is being exhausted, here and here, heat would be exhausted. You would take those absolute values, add them up, and that would be Q sub C. So try not to get confused by the difference. If there's a subscript H or C, you're talking about an absolute value. But for an individual process, Q can be positive or negative. And lastly, I'll reiterate, you may have to add up multiple individual process Qs to get the total Q sub H or Q sub C. This refers to the cycle as a whole. Let's actually calculate Q now for process 1 to 2. The question is, how much heat do you have to dump into a gas, an ideal gas, in order to change its temperature by a given amount at constant volume? That's the definition of constant volume heat capacity. Remember, the heat required at constant volume is number of moles times the heat capacity at constant volume times delta T. So if we could figure out each of these 3 quantities, we just plug them into this formula and we've got our heat. Well, for the number of moles, I'm going to do that off to the side here. I'm solving PV equals nRT for N. That would be PV over RT. Well, I have to evaluate this at a particular state. And the only point on the PV diagram for which I know all 3 state variables would be number 1. So I'm going to use that. And I won't write it down, but remember we start at 1 atmospheric pressure, so that's 1.01 times 10 to the 5th. The volume was initially 50 cubic centimeters, so times 50 millionths in SI units, divided by 8.31, that's universal gas constant, or ideal gas constant. And then we divide by the temperature of 293. So I'm talking about 0.00208 mole. Let me make sure that's, yeah, same number that the book got. I'm sorry, there it is. And I will be doing this in a spreadsheet. And it's quicker that way. But you should get practice doing it both ways because you can't use a spreadsheet for your exam. Well, you could, but you can't turn it in. All right, what's next? Now that we know the number of moles, we can plug that in. Now, what about the heat capacity or the molar specific heat? Well, I neglected to mention, we're told in the problem that this is it's a diatomic gas because presumably it's air inside the cylinder here. Air is a mixture of several diatomic gases. So for a diatomic gas, remember at typical temperatures, how many degrees of freedom? 5. 3 translational, 2 rotational. So the constant volume heat capacity is 5, 1/2 R. Remember, you get 1/2 R for every degree of freedom. And we didn't talk about this much, but if a gas gets hot enough, a diatomic gas, some additional degrees of freedom become available. That's a quantum phenomenon. And then this 5 would go up to a 7. But you can always just assume, unless stated otherwise, that for diatomic gas, you've got 5 degrees of freedom in the normal range of temperatures. And that means the constant pressure molar heat capacity is 7/2 R, because remember that relation Cp for an ideal gas is Cv plus R. So you just add 2/2 R, which is R, and you get 7/2. We're going to need both of those facts. Now, the last thing we need is the final temperature. If we're going to use delta T here, we got to figure out what isotherm is 0.2 on. So again, I like to use common sense now. I've gotten accustomed to thinking about it this way. If you're not changing the volume, if the particles are in the same size box, but you want to triple the pressure, aren't you going to have to triple the absolute temperature as well so that they're all bouncing around? Everything's proportional here to the first power. So the other way to look at that would be, you could say, okay, PV equals nRT. For an isochoric process, V doesn't change. So let me collect everything that does change, that's P over T, and everything that doesn't change, that's this garbage on the right side. So for two different states, points 1 and 2, we could say P1 over T1 equals P2 over T2. We're solving for T2, and that would be P2 over P1 times T1, which is exactly what I just did in my head. I recognize that the final pressure is triple the initial pressure. So this ratio is 3. That means the new temperature needs to be 3 times the initial temperature. And on an exam, you'd want to justify that somehow. Don't just write down the answer, because I'll assume that you're a cheater, especially after discovering that no less than 1/3 of the people in my 3A classes have cheated. Okay, on exams. 293 times, yeah, that's a sad story. Faith in humanity, gone. Well, worse than it was before. 879 is our new temperature. So I'm a little reluctant to draw the isotherm because I don't actually know if it goes through this point. Let me just draw it part away, and then I'll fudge it later. Okay, so this isotherm is the 879 isotherm. Okay, by virtue of the higher temperature, we know that the gas has quite a bit more energy up here. Now, it hasn't done any work yet because its volume has not changed. It's about to do work, but it definitely has more energy because it drew in some heat from the high temperature reservoir. What is the high temperature reservoir? It's that flame. Now it's going to expand. Let me put the arrows so you can recognize we're doing positive network clockwise. A heat engine always goes clockwise on the PV diagram. Otherwise, it would be doing negative work. But we'll look at that too. All right. So let's plug in those numbers here to find the heat. And what I can do is put Q12 to specify it's the heat drawn in during the process that goes from point 1 to point 2. So we've got our 0.00208 moles times the heat capacity of, that's constant volume, so 5/2 R. And I'll point out, your solutions manual made an error. They first said, you can't see it because it's fuzzy. First they said CV is 3/2 R, and then over here they use 5/2. Another typo, see? I wrote, don't! 5/2 R, and the temperature ends at 879 and begins at 293. Let's just see how many joules of heat are drawn in. 879 minus 293. So that's a change in temperature in kelvins, times 5 divided by 2 times 8.31 times 0.00208. Okay, 25.3 joules of heat are transferred into the gas. And what did the gas do as a result? Where does that heat show up? Well, it's not being used for work because the gas does not do work in an isochoric process. It goes into increasing the thermal energy of the gas. Now, the other way to think about it, since I've got this equality here, let me also just say this. Remember that point I kept making in the previous chapter? Even if the process you're talking about is not an isochoric process, it could be an isobaric process, you can still calculate the change in energy using this formula. So I'll emphasize that again. This is not always true. This is the definition of constant volume heat capacity. So this is only the heat required if your process actually is constant volume. But whether it's constant volume or not, this is true. Whoops, I chopped off the end. you can always calculate the change in energy of an ideal gas using this quantity. Again, that comes from the first law here. For an isobaric process, there's no work done. And since the energy of a gas, an ideal gas, only depends on the state, then it doesn't matter how you get from the initial state to the final state. All that matters is what those two states are and their corresponding temperatures. Right? So you can review that in the previous video or in the book, but you do need to know that to solve some of these problems. You can always calculate change in energy by using the formula for constant volume heat capacity. It's not necessarily the heat. That's only true if it is a constant volume process, but it always is change in energy. Okay, we're trying to get to QH so that we can calculate the efficiency. We need the total heat drawn up from the high temperature reservoir, in other words, the flame. But heat will also be sucked up from the flame in this part. We don't have to, whoops, what's this all about? This is supposed to go down. Heat's going to be exhausted here and here. So that's the QC. That contributes to the heat that's exhausted into the cold temperature reservoir, which was that block of ice. We don't need that actually to find the efficiency because we've already found the work. But we do need this one. So let's now look at process 2 to 3. Where do we start? Well, we're in luck here because what type of process is this? Isobaric. So when you are looking at an isobaric process and you need the heat, you should immediately remember, oh, just use the definition of constant pressure heat capacity. The heat drawn up from 2 to 3, since it's an isobaric process, is just number of moles times the molar specific heat at constant pressure times delta T, which is T3 this time minus T2. So as long as the process you're talking about actually is a constant pressure process and it's an ideal gas, then you can go ahead and use this formula to calculate the heat. That's the definition of the constant volume molar heat capacity at constant pressure. What a mouthful. Okay, well, we've already calculated the number of moles. And what about the constant pressure molar specific heat? Remember, that's the 7/2. This is only true for a diatomic gas. For a monatomic gas with only 3 degrees of freedom, there would be a 3 here and a 5 here, but we're talking about diatomic. So 7/2 are, whoops. And then lastly, darn it, we're going to need the temperature. So we also need to know the temperature here. Let's try to do it with common sense and proportional reasoning before we go to the ideal gas. Okay, so the volume actually is expanding this time, and yet the pressure doesn't change. So think of those gas particles bouncing around. The pressure comes from their collisions with the walls. If you make the box bigger, but you don't change the temperature, so the particles are still zipping around at the same speed, wouldn't they collide with the walls less often? So if you kept the temperature the same, but you expanded the box, pressure would drop. So how are you supposed to keep the pressure constant as you expand the box? Well, you would have to speed the particles up, and that means you're going to have to make them hotter. So take a guess. If you've doubled the volume, but the pressure didn't change, what did you just do to the temperature as well? You had to also double it. So all I have to do is take the 879 and double it. Now, if you want to do that with the ideal gas law, go back here. This time, what's not changing? The pressure is not changing. So I'll put the stuff that doesn't change on one side. That would be V over T now. And the stuff that, no, I got that wrong. The stuff that does change is on the left side. And the stuff that doesn't change for an isobaric process is on the right side. So if V over T is always equal to a constant, then that means, what am I to, I'm using numbers 2 and 3 right now. That means V2 over T2 has to equal V3 over T3, and I'm solving for the temperature, and I get V3 over V2 times T2. And there it is. Since our new volume is double the initial volume, we went from 50 milliliters to 100 milliliters, that means the new temperature has got to be double the initial temperature. Remember, that only works for absolute temperatures. Okay, so all I have to do is take temperature at point 2 on the diagram, 879, double that, and now we're at 1758. So let me sketch that isotherm. This is the highest temperature the gas ever reaches. (1758) minus, I'm sorry, I've got, just ignore the stupid parentheses. parenthesis singular. That's 1,758. So I realize this is very sloppy. Here, let me put some brackets here. This is delta T, all of that. 1758 minus 879. That's, of course, that's delta T because I just doubled it. Don't make fun of me. Times 7 divided by 2 times 8.31 times the number of moles. Okay, this time 53 point, I'll just round to 18 joules are absorbed. So the heat from 2 to 3, again, as we expected, it's a positive quantity. The only way the gas could be doing work and yet maintain the constant pressure would be if heat is flowing in to replenish, the energy, the thermal energy that it's losing by doing work. Okay, well, we're just about done because we know that these Q's are going to be negative. You would add up their absolute values to get QC, the heat exhausted into the ice block, which is the cold reservoir, but we don't actually need that to solve the problem. So QH is the heat absorbed from 1 to 2 plus the heat absorbed from 2 to 3. Let me add those two numbers together, plus 53.18. And I find that a total of 78.5 joules of heat are absorbed per cycle. Now, I should be careful there because if you want to talk about the total Q for the entire cycle, then that is not going to be 78.5. This is just the sum of the positive Q's along these two processes. But if I then added the two negative Q's, I would get some lower number for total Q. So there's really like 3 different types of Q going on. I'm going to put Qij to signify the heat drawn in or out for one particular process, like an isobar or an isocore. And then there's the sum of the positive heats, which is what you'd call QH, the heat taken in from the hot reservoir. But then you could just talk about Q total, which I'll call Q. This would be the sum of all your Qij's, and that's not necessarily a positive or negative number. Well, for a heat engine, it would have to be a positive number. So these are 3 different senses in which you might use the letter Q. This can be very confusing. There was a point I wanted to make just a moment ago. Evidently, the highest temperature reached by the gas here is 1758. What does that tell you about the temperature of the flame? Remember, the entire time between states 2 and 3, heat is flowing into the gas here. I really shouldn't have drawn that arrow because it's not like this box represents the gas. That's silly. But during this process, heat is being transferred into the gas from the flame. And remember the second law of thermodynamics. That only happens if the flame is hotter than the gas. Otherwise, the heat would flow the other way. So we know that since heat is flowing in the entire time, including right before it reaches this temperature, that means that the flame must be hotter than this temperature. We don't know what the flame's temperature is, but we do know that the flame's temperature is higher than the highest temperature achieved by the working substance, which in this case is the gas. Now I'm curious now, I'm going to see if number 4 really is on the PV diagram, or excuse me, if it's on the same isotherm as number 2. So let's think about it. Constant volume here. And the pressure is dropping from 3 atmospheres back to 1 atmosphere. So think about those particles bouncing around in the box. The box doesn't change size, and yet the pressure drops to 1/3 of what it was here. How do you get those particles to only exert 1/3 the pressure in a box of the same size? They would have to be at 1/3 of the absolute temperature. So that means I can take 1758, pardon me, and divide by 3, and that tells me that the temperature here is actually 586. Aha, so this is not on the same isotherm as this one. I'm going to go ahead and complete the isotherms here in order of increasing value. This is the 586 isotherm. So if you wanted, you could rank each point in terms of the thermal energy of the gas in ascending order. So this is when the gas has the least energy. Recall that's before the flame was turned on. This is when it has the next highest energy, then this. It's got the most energy right here, which is kind of surprising, right? Because you might think that it's going to have a little less energy after it's done its useful work. Remember, when it goes from 2 to 3, that's when it's expanded all the way It's already finished lifting that box of rocks, as I called it. So it's done doing the useful work. You would think that it would have spent its energy already, but not necessarily. It actually still has the greatest energy at that point. It just means that in the process of getting to that highest energy, it was also doing useful work. So the heat that was flowing in this entire time was doing two things. It was allowing the gas to do useful work, at least during this process, but it was also causing the gas to gain internal energy. Remember, that's what the new version of this first law tells us. When you put heat into a gas, you can allow the gas to do useful work, or you can increase the internal energy of the gas. Okay, we are now ready to determine the efficiency here, because we've already calculated both of these quantities. The efficiency of this particular engine, well, the useful output work we found by multiplying base times height, that was just the 10.13 joules. And we compare that to what we had to pay for from the fossil fuel company, the oil company, or the electric company, electric power, whatever, Southern California Edison. I thought that actually doesn't make sense because we're talking about a heat engine here, which is probably not an electric motor. In any case, we've already calculated QH. Where'd that go? That was the 78.5 joules. I'm making you dizzy here. Okay, how, excuse me, how efficient is this engine? Oops. There it is, 12.9%. So roughly 13, only 13% of the energy extracted from that flame actually went to useful work. So you're, whoever's using this engine, they just totally dumped, carbon into the atmosphere. What do they get for it? Only 13% was useful. Whether they burned wood or coal, a lot of that liberated chemical energy, which now showed up as heat, thermal energy, it didn't even get used to lift the box of rocks. So you might be thinking, there's got to be a way to improve this engine because that's really wasteful. Well, you can improve the engine, but the big surprise in the 19th century, discovered by this guy, Carnot, I was reading about his life. Never married, no kids. I mean, it's not for everybody, but he died fairly young. I forget why. Everybody got some kind of disease back then. I think he lost his mind, ended up in a sanatorium, but he developed the stuff when he was like 27. What was I doing when I was 20? Actually, I was in these classes. What will you guys be doing when you're 27? I don't know. Hopefully not locked down. But we know from Carnot, he's the one who first showed this, that there is a limit on how efficient this engine can be. Now, it's probably higher than this, but it's not 100%. What is that limit? Well, it's really easy. Let me refresh my memory here. The theoretical limit of efficiency for a heat engine, it can only be achieved by these so-called reversible engines or a Carnot engine. We'll talk about that more. I'll put eta Carnot. That's the Greek letter eta, by the way. Here it is. It's 1 minus cold reservoir temperature over hot temperature reservoir. Such a simple result. Very pleasing aesthetically. Easy to use. Of course, you could also write that as the difference in the temperatures over TH. So basically, to maximize the efficiency, you would need the largest possible difference between temperatures. And that is why power plants, they build these giant boilers and giant turbines made out of really strong materials. I don't know if it's steel or what, because you want to be able to subject that equipment to the highest possible temperature, and that implies very large pressures as well. And you want to dump your waste heat into like a cold river, because the greater the temperature difference you can achieve, the more efficient your engine will be. There's a limit to how high you can get that temperature, though. If you make it too high, your equipment's all just going to melt or vaporize. So there are practical limits. But for comparison, what would be the efficiency of a Carnot engine in this problem? Well, we don't actually know what those temperatures are. Remember, all we concluded was that the temperature of the hot reservoir is at least 1758. We don't actually know what it is. What is the temperature of that flame? And the temperature of the cold reservoir, well, think about it. The coldest this gas ever gets is 293. And from here to here, it's still exhausting heat. It exhausts heat from here to here and here to here. So right before it gets back to point 1, it's still exhausting heat. Heat is still flowing from the gas into the cold temperature reservoir. And that means that the cold temperature reservoir has to be colder than 293. So let's choose as our reservoir temperatures the highest possible value for the cold reservoir and the lowest possible value for the hot reservoir. And I'll say eta Carnot, the minimum efficiency. We'll go with those minimum and maximum temperatures. So that would be 1 minus, the cold temperature would be 293, and the high temperature would be 1758. By the way, before I plug those numbers in, do you see that if you could make your high temperature go to infinity, or basically make it way bigger than the cold temperature, this goes to practically 0 and your efficiency would approach 1, or in other words, 100%. That would be the only way to actually achieve 100% efficiency. Now here it is, 1 minus 293 divided by 1758. Drum roll. Whoa, 83%. Way higher than this. So now I am prejudiced. Next time I see a PV cycle that looks like this, I'm going to laugh at it. I know that a rectangular PV diagram corresponds to a heat engine with a really lousy efficiency. All right, so what an awkward shape. This thing is so square. You know, we need some curves in there if we want some more efficiency. We're going to need some isotherms, some adiabats. That's what the Carnot cycle is all about. And you should also be reading in the chapter about the Brayton cycle. I really like that your book emphasizes that, because evidently that's how actual refrigerators roughly work, and jet engines, right? Ubiquitous. Maybe not now. Most of us are not traveling on jets now. So the next thing I'm going to do is go back and redo this whole problem with a spreadsheet, because it's nice to see it done another way, and we can actually be more meticulous and check our results a variety of ways. So one of the nice things about these problems is that you can check your answers, because there's more than one way to get these quantities, and that's demonstrated in the examples in your chapter, and I'm going to demonstrate it also in these videos. Okay, as promised, here is my spreadsheet. You'll notice that I've labeled all the relevant quantities. I'm going to enter them. So I've already practiced with the spreadsheet to make sure that everything comes out okay, but I wanted to show you the process. And if you look at the quantities that are entered here, you could actually use this for a variety of heat engine problems. You know, adapt it slightly if you've got more than 4 processes. So if you'd like this template, just email me. I'll throw it up on Canvas. I'm not going to throw it up until you email me, because I want the satisfaction of knowing that somebody actually wanted the spreadsheet. Okay, let's enter some numbers first. We're talking about a diatomic gas, so first I'll put in the constant volume heat capacity in SI units. I know that that's equal to 5/2, because there are 5 degrees of freedom. And I'm going to put the equal sign, because even though Excel is going to convert this into a decimal number, if I put the equal sign, then when I go back, I can at least see that originally I had it as 5/2. For CP, wait a minute. Hang on a second. Isn't it 5/2 R? Yeah, I did this wrong in my own. Yeah, what I really should have done is, hang on a second. So let's enter R first. That's 8.31 in SI units. So this is really 5/2 times R. Okay. So I'm going to click on the cell for R. See what's happening? I'm referring Excel to the value that I've already entered for R. Great. Yeah, so I did this wrong previously. I'm glad I caught my mistake. For CP, we add R to CV. So instead of 5/2 R, it's 7/2 R. 7/2 times R. And these numbers should look familiar because these show up in tables. Should you have them memorized? No, I don't have them memorized. What you should memorize is how they relate to R, the various multiples. So remember, just as an example, diatomic constant volume, that's 5 degrees of freedom. So it's 5 times R over 2. Well, what's R? It's basically 8. So R over 2 is basically 4. 5 times 4 is roughly 20. So you can confirm these numbers in your head. Over here, I've labeled the various points on the PV diagram. We're given the state variables for the first point. So let me enter those now. This is equal to 1 atmosphere, and I want to use SI units here. So this is going to be 1.013 times 10 raised to the 5th power, 10 to the 5th pascals. The volume was 50 cubic centimeters. That's 50 millionths. And you don't actually need the parentheses. You can just put -6, I discovered. That's in meters, cubic meters. We're told that the temperature is 20 degrees Celsius. Add your 273. Okay, and now we can go over here and figure out how many moles we're talking about. I'm going to solve in my head the ideal gas law for N, so that would be PV over RT. Well, I'm referring to state 1, so that's P1 times V1 divided by the product RT. Now in Excel, I like to avoid parentheses because I don't like those stacked up parentheses. So when I divide by the product RT, I'm going to divide by R. Oh, come on. Why is it? I can't see the cell above it. What a pain. I guess I'll have to type it. Divided by cell C3, it looks like. There we go. And then also divided by the temperature at 0.1. Okay, so this is the ideal gas law that I've implemented. There's our number of moles, same as we found previously. Now, there's a couple ways we could go about filling the rest. First of all, I'm just going to plop in the numbers that we read from the graph. We were told, I'll pause here and go back to the graph. Remember, 0.2 had triple the pressure. So we were given that information. The pressure stays the same up until 0.3. And we know that points 3 and 4 have a volume of 100 cubic centimeters. So I think that's enough information to fill in P and V for all 4 states. The temperatures we'll have to do differently, but P and V, we can just fill those out. Okay, so the pressure at 0.3, that's triple, so I'll say that equals previous pressure times 3. But the volume is the same, because that's isobaric. Now, the pressure at 0.3, remember going from 2 to 3 is isobaric, so this is equal to the pressure at 0.2. And the volume now is double what it was before. So I could just say this equals previous volume times 2. And then this is equal to that volume. You know, there's more than one way to do that. I don't like the stupid error bar because it thinks maybe I'm trying to do something iteratively and I'm not. Ignore error. Stop being annoying. 4. Again, going from 3 to 4, that's that bottom isobar. So this is the same pressure as this one. Okay, now we have to fill in the temperatures. How do we calculate the temperatures? You could do it a couple ways. You could just use the ideal gas law. In fact, I think I'm going to do that. I'll calculate this in 2 ways. First, I'll do it using, put this in italics, I'll say proportional reasoning. So at this point, you know, maybe you've checked out mentally because you've seen enough, you know how the problem works, but it's kind of nice to see this done in different ways. And over here, I'll say temperature in kelvins using ideal gas law. We'll see if we get the same answer both ways. Well, this was just given, so no calculation there. Okay, for proportional reasoning, remember going from state 1 to 2, that was that vertical upwards line that's isobaric. So if you're not changing the volume, how do you triple the pressure? You'd have to triple the temperature. So this would equal the previous temperature times the ratio of the pressure. So that's the new pressure compared to the old pressure. We've seen that number already. Let's try it a different way and see if everything works out. Let's solve for T in PV equals nRT. So this would be equal to PV over nR. So at state 2, I have to use all the variables at state 2. P times V divided by N divided by R. I sure hope this is the same number. Cool. So that's satisfying to see. It's kind of mysterious to me. Like if it all works, no matter how you do it, then there's something going on. It's kind of like in mechanics when you could solve a problem using F equals ma, or you could solve it using conservation of energy, and you always get the same answer. And it's like, whoa, is this magic? Why does it work the same both ways? Well, it's because conservation of energy is F equals ma integrated. It's the same math with the calculus, or the first fundamental theorem of calculus applied to it. So of course it's going to work. If calculus works, then they're both going to work. And I'm assuming there's something similar going on here. Proportional reasoning, going from 2 to 3, that was isobaric. How can you How can you double the volume and yet have the same temperature? Yeah, sorry, double the volume and yet have the same pressure. You would have to double the temperature. So I'm going to say this is equal to the previous temperature at 0.2 times the ratio of the volumes. So the new volume compared to the old volume. We've seen that number, but let's use the ideal gas law as well. T would be PV over NR. So the pressure at this state, or at this point on the PV diagram, times the volume divided by N divided by R. And I'm starting to find this whole process very relaxing. State 4. Remember, we dropped straight down. That was an isochore from 3 to 4. Okay. So what happens to the temperature if we use proportional reasoning? If your box doesn't change size and yet the pressure gets cut down by a factor of 3, that means the temperature also had to get cut down by a factor of 3. So this would be the previous temperature times the ratio of the pressures. That's the new pressure. Wait a minute. This is wrong, isn't it? This pressure here. This is supposed to be back down at the original value of 1 atmosphere. Sorry about that. You probably caught that. Original pressure. Okay. So this would be the previous temperature times the ratio of the pressures. That's new pressure compared to previous pressure. Aha. And once again, stupid error warning, go away. Let's also use the ideal gas law equals PV over NR, pressure at this state times volume at this state divided by N divided by R. So there's your first example of how you can get the same answer different ways, and that provides a good check. So if you've got time left over in your next exam, let's say 3 hours, because you're going to leave minimum half an hour to scan and upload, which everybody did last time. That was good. Take your time to check your results if you want. Now let's get into the calculation of the works and the heats and the change in energy. Remember, we didn't actually have to calculate all these quantities to solve the previous problem, or to solve this problem the previous way. All we needed was the overall efficiency. But let's go ahead and calculate all of these just the same. It's good practice, and you're going to need to do this for other problems anyway. Okay, so I've made 2 columns for the work done by the system in each process because I would like to use 2 different methods and confirm that we get the same answer. So let me pause and remind you of the first law. No, I don't have to pause. I can just do this. The chapter 21 way of writing the first law of thermodynamics. I'm sorry, slipped out. Thermodynamics, something I picked up from an old professor, is, let's see here. When you dump heat into the gas, it could either be used as useful work or show up as an increase in energy. So if I solve that for the work done by the system, that would be Q minus delta E. Here's how you can think about that. How much work is done? Well, just take the heat that is transferred into the gas. That would be the work done, except for whatever amount actually is used to increase the gas's energy. So just take away whatever increases the energy of the gas, and the rest of that heat is being used for useful work. Okay, screen share, Excel, here we go. Back to the spreadsheet. Let's do the heats first, because remember, every process in this problem is constant volume or constant pressure, and we can use the definition of the molar heat capacity. So from 1 to 2, that was the constant volume process. So I'm going to use CV. So that's equals, remember the formula? Q equals NC delta T. So number of moles times C sub V, which I've already calculated, times delta T. Well, delta T would be temperature at 0.2 minus temperature at 0.1. So parentheses T2 minus T1. And you're seeing now the advantage of the spreadsheet. Doesn't that number look familiar? So during that isochoric rise in pressure, heat was flowing in from the flame. This is how much heat. Now, the work done is 0. So this is trivial. We just know that there's no change in volume, so I'm going to enter 0. I could do it that way. Or I could actually, since You know what? This is, I should have written this equals P delta V. That's only applicable for a constant pressure process. So I probably shouldn't have labeled it that way. So maybe I'll just say alternate. Because it's really going to depend on the process. But this one's trivial. We know no work is done, so I'll just leave that blank. And in this case, Q and delta E are the same. If you go back to the law, written this top way, if the gas is not doing work because its volume's not changing, then all of the heat is used to raise the temperature. So those two quantities would be equal. Excuse me. So I'm just going to say delta E is equal to Q. And I'm really using the first law of thermodynamics. So I'm going to have different justifications for each of these processes. Okay, 2 to 3, that was the isobaric process. Well, let's do the heat first. Remember, if it's a constant pressure process for an ideal gas, you can go ahead and use the definition of constant pressure molar heat capacity to find the heat required. So this would be equal to the number of moles times constant pressure, molar heat capacity, times the delta T's. Well, now it's T2 and T3, so the final temperature is T3 over here, minus T2. Okay, so this is the heat taken up by the gas during that isobaric expansion. So while it's doing work, while it's lifting that box of rocks, it's taking in quite a bit of heat there. The work done, okay, well, let's do this different this time. Instead of using the first law to find delta E, I'm going to do this. Remember, for an ideal gas, regardless of whether the process is actually isochoric or constant volume, you can still use the formula for constant volume heat capacity to find the change in energy. Because remember, the energy of an ideal gas only depends on the temperature. So you can imagine that you've got between the states by using a constant volume process and find the delta E that way, even if it wasn't actually constant volume. So this is equal to, and you may forget the justification there, just remember that you can do that. Delta E can always be calculated using CV. So it equals the number of moles times the constant volume, it's got to be CV, times the change in temperature between 2 and 3. So T3 minus T2, there it is. And here's where I'm going to use the first law to calculate the work. Remember, the heat that flows in is divided into two possible effects. It could raise the energy, or it could do useful work. So the useful work here would be the heat drawn in minus the quantity that was used to raise the energy of the gas. That's the work done. And watch how cool this is. Let's confirm that. Remember, in general, work done by the system is the integral of P dV. It's the area under the PV curve. But for an isobaric process, P is constant. You pull it out in front of the integral, and you just get P delta V. So this is equal to P delta V. That's the pressure between 2 and 3. I can grab either cell because it's the same, times the change in volume. So final volume minus initial volume, and this better give us the same result. Pretty cool that it does. 3 to 4, this is another isochoric process. No work done, that's easy, trivial. And remember, if you're trying to find the heat required to change the temperature of a gas at constant volume, well, that's the definition of constant volume molar specific heat. So this equals number of moles times CV. I can do this for the heat because it is a constant volume process, times delta T. This time it's T4 minus T3. Now you see the temperature is dropping, so we're going to get heat flowing out. Remember, as you drop from 3 to 4, you're exhausting heat. This is the number of joules that are dumped into the ice block as you go from state 3 to state 4. Once again, I will use the first law of thermodynamics. How do the signs relate here? Let me go back to the formula here. For an isochoric process, work is 0, and we get that Q equals delta E. Makes sense, right? If Q is negative, heat is flowing out, and that means the internal energy is dropping. So I'm just going to set this equal to Q. I could do that, but again, let's be clever and try to confirm it. let's use the formula. Remember, you can always calculate delta E using CV if you want. So that's if you happen to know the delta T. So this should be also the same as N times CV times the temperature change. So that's final temperature of 4, T4 minus the temperature of T3. Same number. Totally different ways of calculating, right? It seems like, how does it work like that? I don't know. I know this stuff, but I don't know it well enough to see why all of this works. If I ever get to that point, then I could say that I TLU freshman or sophomore level thermodynamics. TLU is an acronym that a friend of mine coined years ago. It means transcendent level of understanding. I don't feel that I yet TLU this. F equals MA, I definitely TLU that after repeating it ad nauseum. 4-to-1. This is the isobaric compression at the very bottom of that rectangle. This is the gas getting compressed back to its initial volume so that it can start all over again. How do we calculate the work from the first law? Well, we need the other two quantities first, so we'll come back to that. Again, this is a constant pressure process, so we can find the heat using the definition of constant pressure heat capacity. So this is equal to number of moles times Cp, excuse me, times final minus initial. Well, the final temperature, we're back to T1 minus T4. You'll have to excuse me. Sorry, a lot of talking. This video is really dragged on, has it not? This is the heat exhausted during that last process. If you wanted to find QC, the total heat exhausted, you would add up the negative Q's. Now, delta E. Let's go about this a couple different ways. Let's first find the work done using P delta V, because if pressure is constant, pull it out in front of the integral, the work done is just P delta V. So this is equal to the pressure during that isobaric process. I could use cell 4 or cell 1, doesn't matter. So pressure times final volume minus initial. Well, the final volume is the initial is the at state 1, and the initial volume for this process was at state 4. That doesn't look right. P delta V. H5, it looks too small, does it not? H5, okay, which is the pressure, times I2 minus I5. I2 minus I5. Okay, I suppose I did that right. Let's, yeah. Now we'll use the first law. So I'll go back to my notes just one more time here. How do we get delta E from the other two? If we solve for delta E here, delta E is equal to Q minus the work. Again, how much did the energy rise? Well, it would have risen by however much heat was absorbed, but some of that heat went to do useful work. So I'll take the heat and subtract the work done. So I gotta go back to Excel here. We're almost done here. Okay, take the heat and subtract the work done. And I find that the energy decreased yet again. Okay. Let's, as a check, I'm not actually going to make a new formula or a new row here permanently. Let's just do a check here. Instead of using the first law to get delta E in terms of work and Q, let's instead use CV to find delta E and use that to calculate work using the first law. So ignore this net over here. I'm going to check the result and then I'll just erase it. We don't need to recalculate the heat. But here I will say delta E will be NCV delta T, because that always works. NCV delta T. So that's final temperature at state 1 minus the initial temperature at state 4. What am I doing wrong here? C48. C40. I'm totally blanking out here. This is supposed to be number of moles. That should be C4. Okay, so that 8 is spurious. I don't know why I entered that. Hey, I think that was the same. It is the same number. Great. Okay, so now we can use the first law to confirm the work. Well, the work would be whatever the heat absorbed is minus the amount of that heat that went to raising the energy. Yes, how satisfying. So it's a nice check. Now let me get rid of these since we've convinced ourselves that thermodynamics, at least in this book, works. And now let's add everything up. To find the total output work, you just add up all the works. Simple as that. So this is kind of redundant. It's like I'm going around in circles. I didn't actually calculate the work in this cell using the first law, so I'll just refer to the other value for the work. Okay. So the net work done would be the sum of all the work. Sometimes the gas is doing positive work while it's expanding. Sometimes it's doing negative work while it's being compressed. The total output work would be the sum of all these works. And I believe we did do that already when I solved this problem on paper. So in one cycle of this heat engine, it does 10 joules of work. And that work had to come from somewhere. It had to come from the overall heat absorbed. So let's find the total heat drawn up by the reservoir. That would be the sum, I'm sorry, not by the reservoir, by the heat engine, the working substance. It would be the sum of all the heat, some positive, some negative. And there it is. So even though some of the Q's were negative and some were positive, the net heat taken up in one cycle is 10 joules. Those 10 joules were used to do 10 joules of output work. Now, what should be the change in the energy of the working substance during one cycle? The whole point of a heat engine is it's cyclic. It's got to return to its original state. And if it's in its original state, then the energy is the same as it was at the beginning. So there shouldn't be any change in energy overall. So I sum all these delta E's up, and we know that we should get 0. Great. Now look at this last line. Again, don't be confused. This is not the work and the Q over any one process. This is for the entire cycle. You can also use those symbols, W, S, and Q, to talk about the relevant quantities for the entire cycle. And the first law of thermodynamics should still apply in that sense. So if I go back to my notes, Q equals WS plus delta E, we found that the total change in energy is 0 for a cyclic process. So the heat has to be the same as the work done by the gas. You can't just do the work for free. It had to, that energy, the work done by the system during one cycle, had to come from the net heat taken in. And I think we should check one more thing here before I sign off with this problem. Can you believe how we've exhausted this problem? All right, we do need to calculate the efficiency here. And yeah, I'll do it this way. Efficiency equals the output work, which is the net work done. You don't have to worry about pluses and minuses there. It's just the sum of all the works. So that's the output, the useful output compared to what we paid for. Well, QH, the heat taken in from the hot reservoir, you had to pay for those fossil fuels to make the fire. Yeah, maybe you're thinking, wait a minute, don't you also have to go to the grocery store and pay for the ice block? No, because real heat engines usually just dump it into a river or something like that. Now, Dr. Seuss taught me when I was a kid that that's bad, but Dr. Seuss was a communist, so I'm not really worried about that. I mean, it's just warm water, right? It's not necessarily polluted water. Of course, it could throw off the ecosystem or whatever. I don't know. QH would be the sum of the positive Q's. So I go up here. I've got 4 separate Q's for each process. I'm just going to add the positive ones. Those constitute the heat drawn up from the hot reservoir. What are we expecting? 12.9? All right, rounded to 2 sig figs, it's 13%. That's great. Just the same answer we got before. Now, as a check here, remember for a heat engine, let me go back to the notes here. For a heat engine, the total heat drawn from the hot reservoir goes to 2 parts. Some of it is useful output work. I'm going to call that work out, which is really the sum of all the WS's. I could have called that, instead of W net, I could have called it work out, plus whatever's exhausted to the cold reservoir. And remember, this is always a positive number. This is always a positive number. Let's check that those are consistent using the spreadsheet. I'll do that here. QH. That would be equal to the sum of the positive works I'm sorry, not the positive works, the sum of the positive Qs. Okay, so 78.5 joules were absorbed from the hot reservoir, and then how much heat was exhausted to the ice? That would be the sum of the negative Qs. Okay. Oh, right. Remember, it's got to be an absolute value. I'm glad I'm doing this. Absolute value of the sum of the negative Qs. All right. And then work output, W out. That's just the sum of all the works. So I've already calculated that. That would be W net. And yeah, I'll put the word check down here. Let's check that the sum of QH and QC is in fact, that the sum of QC and work out is in fact QH. So I'm going to check that for the value of work out plus the heat exhausted to the cold reservoir. So work out, of course you see that it works, but it is equal to the heat taken up from the hot reservoir. So there's a lot of pitfalls here. I think the most confusing thing is distinguishing the temperatures of the reservoirs from the temperature of the working substance. The working substance is going through a whole range of temperatures as it goes around its cycle. But the hot reservoir has always got one temperature, the cold reservoir always has another. The high temperature reservoir has a temperature that's greater than the greatest temperature achieved by the working substance at any time. The cold reservoir has a temperature which is less than the temperature of the working substance at any time. Now, those statements that I just made, that sentence is only true for heat engines. If you're looking at a refrigerator, you'd have to make a different statement. I'll save that for another problem. So it's confusing. And this Q, you can use Q for different things. You can use it for an individual process, in which case you want to label it like Q23, Q34. You can also talk about the net Q for the whole process, which is in general not zero. And then you can also talk about QH and QC, which are positive numbers. So the more practice you can get, the better. I hope this was helpful.